All right, section 4.4 is called the definite integral. And I want to start with the definition, and the definition is exactly what this section is defined to be talking about. If we have a function f, and it is defined on the interval from a to b, it's called the definite integral of f from a to b. And the notation are two different notations you've seen before, almost, and they're a little bit related now. In fact, we're related with an equal sign in between them. So notice the notation on the left here. That looks like something we did in 4.1, doesn't it? Except what's different?
It goes from A to B.
Yeah, there's a value on the bottom of it and a value on the top of it. It has an A at the bottom and it has a B at the top. That's different. We didn't have that there before. Okay? This notation here on the right also should look familiar. That summation looks familiar, right? And in fact, the right-hand side before the limit, I know, ignore that for a moment, looks a lot like those summations we were just doing back in section 4.3, don't they? I've got a bunch of heights added together and then multiplied by delta x. And then what I was just explaining when we were looking at the computer screen was this idea of taking that limit and letting there be infinitely many rectangles. That's what this n going to infinity means, is we have infinitely many rectangles that are appearing as we do this. So whenever the limit exists, this works whenever the limit exists. It is the same for every evaluation point C1 to Cn. That's the idea of when those widths of those rectangles become infinitely small, right? They go to 0, that the left endpoint, the middle point, and the right endpoint, they all converge to the same point. That's what that C1 to Cn is talking about there. And when the limit exists, we would actually say then that f is integrable on AB. And integral exists. Okay? That's the notation for what we're doing. Now, we're going to be doing this a little bit differently in this section. Some of you I know have had some calculus before, and so you look at the left-hand side of that thing and you say, well, I know exactly what to do with that integral from a to b of x dx. Hold tight. You can't do it yet. We'll do it in 4.5, okay? Those of you who don't know what I'm talking about, hold tight. I promise I'll tell you next time. But neither are we going to do a whole lot with the summation notation on the right. Your book actually talks about this both in at the very end of section 4.3 and the beginning of section of 4.4. And we're not going to work too much with that limit notation either. But it is important for you to realize that what is really happening here is that these rectangles are getting infinitely narrow. They're just getting infinitely many rectangles. These rectangle process that we're doing, I didn't say it in the last section, but it's called a Riemann sum. So if you've heard of Riemann before, that's the same guy again. Riemann sums are what you're actually doing when you're summing those rectangles together. We have a couple of theorems and then we're going to do some problems. So we might want to know, well, when in fact do we have a function that's integrable? And there are lots of ways of doing that, but for sure if we have a function that's continuous, it's integrable. And nearly all the functions we're working with, I'm trying to think if I can give an example of any right now. We may see some in the next section, but right now all the functions we're working with in this section are going to be continuous. So they are going to have an integral. They're going to be integrable. And then we have some other wonderful rules down here, and they look an awful lot like some summation rules you've seen before. I wonder why, because these are just sort of a one step beyond summations, right? They're limits of summations, so that's why they look very similar. They also look like some of the things we did when we did limits, which has been a long time ago, I know, but because we're looking at limits again, it makes sense that these kinds of theorems would come back up again as well. So if we have a function here on part 1, where we have c times the function f of x and d times the function g of x. Now we talked about section 4.1. What that means is that we can do these integrals separately, right? Remember doing that? Where we said, oh, we can just find the integral of the first piece, we can find the integral of the second piece. We did it when we did derivatives. We talked about it again when we talked about sums in 4.2. So the same idea of being able to separate them has come again. Not only that, but that constant multiplier idea has come about again too. Right, the idea that I can pull the constant multiplier out to the front. Now, we didn't talk about it quite like that in section 4.1, but we did talk about it when we talked about limits, right? Talked about this idea that c doesn't really affect the integral. We can take the integral and then we can multiply it by c afterwards. That's all that this is saying. And we can, so we can separate these into these pieces that do that. Okay, so you've got that constant multiplier rule and that sum rule all in the same sort of statement as under number 1. Number 2 is a little bit different, though. Number 2 says if I have C and it's between A and B. So visually what you have is you have sort of a number line picture, and you've got A over here on the left, you have B on the right, and C is somewhere in between. It doesn't have to be evenly in between, just somewhere in between. All this is saying then is if you want to take and find the definite integral, which is the area under the curve, from A to B, well, you could just find the area from A to C, and then find the area from C to B. You could break it into two pieces if there was a need or want for you to do so. That's all that's saying. Do you guys follow that okay? I know, they're not in order. They should have put them in order, I agree. So in other words, if we wanted to find the whole area right here, and for some reason we wanted to, we could break it into these two pieces and find these two pieces areas individually. Does that make sense? Seems reasonable. The nice thing that this actually has the ability to do for us is if we had a function that had like a hole in the graph at C, we could still find the area here from A to C and the area from C to B without having to worry about that discontinuity in between. That's a very friendly feature, okay? So that's one of the cases where we might see that being used or want to be able to use that feature. I'm going to do several examples, and they're going to feel a little bit disconnected. I promise they'll all come together once we've looked at all of them. You'll be able to see some of the connections between. The first one talks about an interpretation. So when you hear the word interpretation, what does that mean to you? When somebody tells you in some other class to interpret something, what are they asking you to do? Okay, so you said say what you think about it. What'd you say, Kirian? Meaning or value of it. So meaning, I like the word meaning there. We're not going to actually evaluate this particular one, but we are going to find the meaning. We're going to explain what we think about it. So in fact, that word explain means we're going to use something like words, right? We're going to use words. I know you don't think words go with math, but they really do, I promise. We're going to give a verbal description of what's going on. Now, in order to do that, it would really be helpful for us to look at a picture to talk about it. Does that make sense? You can reference the picture in your verbal description as well if you'd like, but at least in terms of describing it, it's going to make a lot more sense if you know what you're looking at to describe it. So grab your calculator if you would, and I would like for you to graph this equation, x cubed minus 1. And I want your graph to go from x equals 0 to x equals to 2. All right? So as you're looking at this graph, you need to make sure that your window starts at x equals to 0 and ends at x equals to 2. So somebody tell me some word pictures of what you see.
It's curved.
It's curved. Okay, what else? It's concave up. What else?
Increases from 0 to 2.
Increases from 0 to 2. What else? Where does it start? Yeah, there you go. It has an x-intercept. But tell me about the y-intercept first. The y-intercept is negative. So I'm starting the graph beneath the curve, right? Beneath the x-axis, yeah? Where exactly does it start? Can you tell me that? -1. Right? So it starts at -1. And you said something about an x-intercept. Where is the x-intercept? Can you tell? It is at 1. Graph's supposed to go over here to 2. What happens when x is equal to 2? Well, as we go beyond 2. But what happens at x equals to 2? What's the y value when x is equal to 2? It's what? It's 7. Okay, so it's above the x-axis, and if not considerably above, at least above enough that it's further above than this x equal to 1. So let me move my x equal to 1 up a little bit. Or my -1, excuse me. Just to give us a little bit more accurate reflection of the disparity between them. So we're looking at something like this, right? It's just a little bit below, and then it's a lot above. Does that make sense? You guys are telling me it's concave up, so I'm thinking that I'm looking at something like this. Does that sort of look like what you see? Okay. And here's the deal. This picture does something different than the last section that we did when we were talking about these images. The last section that we did not cross the x-axis, did it? That's a little different. Because what we were doing is exactly what we're going to be doing here as well, except that it was all area that was above the curve, which means it was all area that was positive. Now that feels sort of strange to describe it that way, but as we calculate this a little bit later, what you're going to find is that this piece right here it's going to show up in green here. This piece right here is negative area. It's area that's under a curve. Okay? And then this piece over here is considered positive area. I probably shouldn't have used red. Red is usually used for negatives. How about we use black? And then I'll go back and use red over here. So your book refers to this as signed area. Why are you guys laughing? Okay, you want to tell me the joke. All right, so this is signed area. So your calculations are going to refer to this as negative area. And they're going to refer to this over here as positive area.
So when you say it's under the curve, are you saying or over the curve? You're saying it's
That it's under the x-axis. I'm sorry, I'm using the phrase incorrectly. It's under the x-axis.
Okay.
Yes. So if your curve is under the x-axis, then the area between the curve and the x-axis is going to be area under the x-axis. This will be considered signed area that's negative. This is signed area that's positive. This is important to realize because if we calculate the integral from 0 to 2, what it's going to do is it's going to give it, I call it the net change in the area. What it's really going to do is it's going to find for us the positive area and the negative area, and it's going to add them together, which means it's not finding the total area. Do you guys understand that? It's basically going to find what we think of as area up here. It's going to take this and it's going to add this, and it's going to find this area and it's going to subtract it because this is negative area. It's kind of strange. So if we were actually finding this particular description, it might look something like this. This is the difference in the area trapped between the curve. That does not look like curve at all. Let's try again. And the x-axis from 1 to 2. That's why we looked at that x-intercept being 1 and the y-intercept, or and the x ending point being 2. And the area trapped between the curve and x-axis from 0 to 1. That's what it's really doing. It's finding the difference in these two areas. That's what this will do. If I calculate this quantity, and I'll show you some cool tricks in your calculator. Your calculator will calculate that quantity just fine for you. But what it will actually be calculating is it will be finding how much area is there from 1 to 2, and how much area is there from 0 to 1, and it will be subtracting those two areas. And wherever the area is more, in this case above, it will be a positive because it is above the x-axis. If I'd had more area below, I would be getting a negative because there's more area below the x-axis. So I'll show you a couple cool calculator tricks after a couple more examples, just so that you're aware of them. All right, let's take a couple more of these, though, before we quit on this section. These are pretty quick ones. This one says we're going to write the given total area as an integral or sum of integrals. Again, a picture is going to help you to be able to do this. It asks us to find the area above the x-axis and below the curve. So you need to graph this in order to do that. And it doesn't tell you x goes from 0 to 2 or whatever. It doesn't tell you on this one, right? So you don't know what x needs to go from until you look at the graph. So this is a shape you know, though. It's a shape of a parabola opening downwards. And what is its y-intercept? 4. All right, so the basic image that you have in your mind and or on your computer screen, your calculator screen, looks something like this, right? And this description says I want the area above the x-axis, right, above x, and below the curve. which means it wants this trapped sort of hill shape in the middle here, right? That's what it wants. So the image that I'm trying to find the area of is right in here. Well, what I have found out is that I can write that notationally as an integral, but the integral needs to have a lower limit and an upper limit. That lower number and that upper number, where do those come from? The x-intercepts in this case. It's where you start and where you stop finding the area. So yes, on this one it is the x-intercepts. So you need to be able to find from your calculator or from doing just a little bit of quick algebra, what are the x-intercepts for this function? They are -2 and +2. So we write the left one first and we write the right one second. The left one is below, the right one is above. Okay? So in general, and we'll talk about when this is not the case, but in general you'll see the lower value lower and the higher value, the larger value higher. And this is of our function. Our function is 4 minus x squared. Parentheses or not, I'm not going to be too particular about that, but you do need that dx on the end, for the same reason we did before. That dx tells you with respect to x. That's my variable in this function. That's it. That's the notation for this particular picture. Any questions on that? Like, you get to do one of these as a homework problem. You think you can handle it? I think you have 2 of them, in fact. All right, we're going to do one more. This one's going the other direction. They give us the picture, and they want us to sketch the area that corresponds. Okay, this is exactly the opposite question, right? So grab your calculator. You're going to take the equation x squared minus x. You want the graph to go from 2 to 4, but just for perspective's sake, you probably want to see some of the axes in there. So I would suggest you start at x equals to 0, as a minimum, and go out to 4, and recognize that it's only the second half of that picture that you're actually going to be concerned with. Because when you don't have axes in there, things look weird. You really just don't know how to draw the perspective of what's happening. So my picture is going to start at 0 and go out to 4. And if you're careful in how you draw your picture, it looks like you've got a little bit under the x-axis, and then it goes above. Does that look right to you guys? It actually looks fairly similar to an earlier one that we did on example 1. So it looks something like that. Might be a little bit less like that. Maybe like that. Might be a little bit better. 2 is somewhere in between. I kind of need to know what the x value of 2's y value is. I mean, is it actually above the curve or is it below the curve, just so that I really make sure that I get my perspective correct. When x is equal to 2 in that equation, what do you get? You get 2? Yeah. So it really is above the x-axis here, right? So my graph really goes from this x equals to 2. And then what is the value when x is equal to 4? 12? So this is going from 2 to 12. That is, the y values go from 2 to 12. And then what we're supposed to be drawing, you're supposed to be sketching the area. Well, I don't have any area here yet. What do I still need to do to sketch the area? You need to shade it in. And we're not going to draw rectangles anymore, because the idea is that we've let our rectangles become infinitely small so that we actually have the area that we're looking for, which is all of it below the curve and above the x-axis. That's the area from 2 to 4 on this particular equation. Is that okay?
You shade it in.
And you can shade it in.